Hello everyone, welcome back to Chemistry 3120. Today's lecture 27, and today we're going to talk about conjugate substitution reactions. So we finished this last one on naked electrophilic enones, and let's talk about conjugate substitution reactions. All right, so you already know very well what a conjugate addition, what a conjugate reaction is. We're going to talk about conjugate substitution reactions. And I want to first show you some examples where we could use electron deficient alkenes. And let's just start with an example. So let's call this reactions. Reactions with electron deficient alkenes or enones. So if we start with this compound here, this is actually called acrylonitrile. At first glance, you can see that you have some electron deficient or electron withdrawing groups. You have this nitrile group here, which is moving electron density away. And you can see that this is very similar to some of those enones that we've seen previously, in which this carbon here is electrophilic because it is through a 1,4 type of conjugate addition. So you can imagine a nucleophile could react here, then you could move electrons into that nitrile group. So if we take something like, for example, diethylamine, we have this nitrogen here with a lone electron. So you can imagine this could react, and you could get that addition just like I was talking about. So if that happens, we are going to get your nitrogen is now positive. And we're going to now do a proton transfer. So you can imagine the diethylamine is actually also an appropriate base. So now you're going to have sometimes people draw these carbons as a dot to imply that it's linear. In this case, or you could just draw a carbon like I'm showing you here. And then lastly, this will come and then pick up a proton from the conjugate base of the diethylamine. So that's just something that we protonated there. So your final product would simply be this. Okay, so fairly straightforward. This is a secondary amine. If we apply the same principles of this type of reaction to a primary amine, what kind of reaction will we get? So we take methylamine. You can imagine this will come and react. And then we'll do proton transfer. Here I'll just show a generic base, Bronsted base, but that could of course be your methylamine. And then this will come pick up a proton from the conjugate acid. And that would be maybe your final product, right? But what do you think? Do you think it's going to stop there? Or do you think this compound could continue to react? We've gone from a primary amine to a secondary amine, right? Which is similar to this one. So another molecule of acrylonitrile, which is very electrophilic, will react. So it's one of those types of reactions where you can't stop it, even if you try to control the stoichiometry. So another molecule of acrylonitrile will come in. This will react, and I won't go through that mechanism, but it's analogous to what we did on the first part. Okay, and there you have a sort of a dye-substituted amine. All right, so now you understand how this works. Let's take a look at perhaps a more practical example. All right, so we have an aromatic group, and then we have this allyl group with a nitro group attached. What do we know about nitro groups? Nitro groups are very good electron withdrawing groups. If we treat this with sodium borohydride, in methanol, how will that borohydride react? Well, where's your electrophilic center? Your best electrophilic center is going to be right here, right? You can imagine you have 1, 2, 3, 4, or 1, 2, 3, 4. That's electrophilic. If you do react it here, this is in conjugation. However, if you do that, you do break the aromaticity. So this is a much easier electrophile to break. So in terms of a mechanism of how this would work, here's your borohydride. This will come and react. Electrons will move up into that nitro group. And then we're using a protic solvent like methanol. Remember, sodium borohydride works well in protic solvents. Then you'll pick up a proton from methanol. And then your final product will be this reduced form. So it's a very good way to reduce these types of double bonds in the presence of things like aromatic species, but it's only going to occur when you have a good, strong electron withdrawing group. So I'll just draw the final product again, just so your notes are complete. And there's the mechanism there. So these are just some examples of reactions that look like, Michael acceptors to what we've seen before, but they're slightly different because of their electron withdrawing group arrangement. Now let's switch gears a little bit, or move to the next step and talk about the focus of this chapter, which is conjugate substitution reactions. So what we're going to do is we're going to take similar types of structures here, but put a decent leaving group at that beta position. So I'll give you an example. Okay, so here's a compound here. If we treat this compound with something like methanol, let's think about what we've learned already. Okay, this is a good Michael acceptor, right? Because you have this 1, 2, 3, 4. This is electrophilic, and your methanol could act as your nucleophile. So you can imagine this would react here, and you're going to now do that conjugate addition like we've learned about. Don't forget your positive charge on the oxygen. And now we're going to do a proton transfer. So we'll take another molecule. We're in a protic solvent, so it's very simple to remove this proton. Again, intermolecular proton transfers will happen much more rapidly than intramolecular proton transfers, even if it's a 5 or 6 membered ring. There's too much of an energetic barrier to rotate the bonds and align them perfectly. And since we're doing this in methanol, that just happens super fast. So, do a proton transfer. And now the oxygen can come down, reform that ketone, double bond forms, and your better leaving group is a chlorine. So the chlorine's a good leaving group. And then what you're going to end up generating is this compound here. So conjugate substitution reactions work if there's a good leaving group at the beta position. Okay? All right, so let's take a look at an actual example of a molecule that we could make. I'm going to erase this whole board because after this lecture will be done all this stuff on the microreaction. So I'd like to use this board space. All right, so let's make this compound here. That's a 3. Let's make this. Let's make this from this starting material. All right, so from those two molecules, we'll also add some other ingredients along the way. This is a double bond. Okay, so write that down. I'll get a brush to erase the whiteboard. Think about how you could put those together. So you can see here that we need to form a nitrogen carbon bond here. Here's our nitrogen, here's a carbon. And it's set up nicely because you can use that conjugate substitution reaction like we just talked about. Because the nitro is a good electron withdrawing group, so you can imagine the electrons come here, they come down through the nitro group, come back, reform that double bond, and then these thiol methyl groups are actually pretty good leaving groups. Okay? So after you do that first reaction that first time, when these two react, you're going to end up generating, so here's the arrow showing when these two react. we're going to generate this compound here. So one of the thiomethyl groups left, but the product has an NHCH3 on this side, another one. So what do we need to do to complete that product? So we need to do another conjugate addition reaction. So it's going to react here, electrons will go through the nitro, come back, kick that off, and you want that group to be methylamine, right? So we treat that with this, and you'll get your product. So if you're not convinced, go through the mechanism so that you understand each step. Just a fun fact, this is an anti-ulcer drug. This one is called, it's one of an older medication. It's called Zantac. And this is how it's synthesized industrially. All right, so we're going to switch gears a little bit and talk about something called nucleophilic aromatic substitution. You've certainly heard or seen this before, probably in second year organic chemistry. But we're going to look at it using our understanding of conjugate addition. Okay, so before we start talking about nucleophilic aromatic substitution, let's just go over a few basic principles. All right, so recall, if we have something that looks like this, and this is not aromatic, and if we treat this with something like hydroxide, there's a few different things that could happen. You know, bromine's a good leaving group, so you could do direct SN2, or it could perhaps go via SN1. It's sort of on that fence there with respect to stability. It's not really substitute, so I would probably say SN2. But you could also get a competing reaction where you could actually eliminate and form like a double bond. But let's just focus on what that SN2 product would look like. And it would just be literal substitution like that. Okay, so nothing too surprising there. However, you know that if you take an analogous type of compound, but this time like a bromobenzene compound, and if you treat this with hydroxide, you're not going to generate phenol, right? This is not going to occur. It doesn't occur because the big difference is that this is an sp2 hybridized carbon, right? And if we're doing SN2 chemistry, you can't do direct displacement SN2 chemistry on an sp2 carbon. Okay, so are there other ways that we could do some type of substitution on aromatic compounds? So, you know, there is one other way to do this, and this is if you have some group, let's call X, and rather than going through SN2, if you have a way to make X a really, really good leaving group, and we'll look at an example later in this lecture, what you end up doing is you can form this sort of empty orbital with a positive charge, and then some type of nucleophile could jump in. So this doesn't go by SN2, but goes by SN1. But in general, this occurs, you know, really quite rarely. It's really rare. And it's not practical, and it's not something that we could rely on as organic chemists. But it's definitely a type of reaction that we want to do So how can we do this? How can we get around it? So before we talk about nucleophilic aromatic substitution exactly, let's look at some of these types of examples and apply it to the setting. So here is a compound with our nitro group that we've seen already a few times today already. And if we treat this with like a secondary amine disubstituted, you know, right, just from what we've been talking about today, that you'll get electron density through this conjugate addition. Electrons will go up into that nitro group. Okay, we do a quick proton transfer. So your base will come, remove that proton. Just going to remove this hydrogen here. It's still here. You know that it's still there. But we don't need it when I draw it. Okay, so then we have this compound here. And then essentially what's going to happen, we're going to move electrons down, electrons will get pushed out, and then we'll release off the fluorine, the F-, the fluoride. And your final product will look like this. Okay, so pretty straightforward. We've talked about similar examples before. If you apply the same principle to an aromatic compound, do we get the same thing? So if we take an aromatic compound, and if we have a fluorine group here, and then we have a nitro group here, and if we treat this with some type of nucleophile, and let's use the same nucleophile, you can see here that even though this is aromatic, this looks exactly like the type of conjugate addition reaction setup that we want to use, right? 1, 2, 3, 4. That's electrophilic. So if that happens, you can imagine you get reaction occurring here, electrons come up, just like we've done before. Positive nitrogen, and again, just like we've done on top, your base comes, does that proton transfer. Let me just fix the structure. So this came here. Make sure you fix this in your notes. Electrons come here, move up. It's drawing too quickly. Okay, so that's your intermediate. So your next intermediate will look like this. So we've broken the aromaticity, as you've seen. And now the electrons from one of the oxygens comes down, pushes and re-aromatizes, and then F- will leave, and this will be your new product. So this is elimination. And really, what happens here is you have, as I mentioned, loss of aromaticity. All right, so the real driving force to letting go of that F is elimination, so you can re-aromatize. Okay, so the electrons from the ring must be able to delocalize the electron withdrawing group. So you could use this on an aromatic system like this, if you want to do something like nucleophilic aromatic substitution. You could potentially have X equals to fluorine, or halogen equals to fluorine, and then as long as you have a nitro group that's in the right position in conjugation, you could sort of do this type of chemistry. You say, okay, that's great, that makes a lot of sense, but let's talk a little more specifically about the role of carbon-fluorine bonds in organic chemistry. All right, the role of carbon-fluorine bonds in nucleophilic aromatic substitution. Okay, so you might be thinking, you know, fluorine, I haven't really seen that as a good leaving group, right? Throughout all, think of all what you've learned in organic chemistry over the last couple of years. You know, have you seen these types of reactions? All right, so let's look at sort of a standard CH3X, where X could be one of the halogens. So this could be fluorine or chlorine, Br, bromine, or iodine. And if you have some kind of nucleophile, you know that you could set this up for SN2. Okay, so if you do this reaction works best if you use things like chlorine, bromine, or iodine. Iodine is actually best because it's such a, you know, it's a better leaving group. You can delocalize the negative charge over this large atomic radius. But if X is equal to F, it will not work. So F minus is a poor leaving group. Okay, and you've probably never seen like methyl fluoride as an electrophile. Similarly, if you look at carbonyl chemistry, we've done a lot of work this term on things like acyl chlorides, acyl halides. So you know that if you do have this type of structure here, and then your nucleophile comes in, and then electrons go up, come back down, X will work if you have things like chlorine, bromine, even iodine, but if X is equal to fluorine, it will not work. Right? You've never seen like a methyl, like a ketone with a fluorine group attached to it. It's possible, but it's rarely used. Okay, so it's a very poor leaving group. Okay, so that's kind of interesting. And one of the reasons is that the carbon-fluorine bond is actually a really strong bond. Even though fluorine is the most electronegative element on the periodic table, we've talked a lot about that, because of its size overlap with carbon, it forms a very, very strong sigma bond. So for example, things like Teflon that are polymers of carbon-fluorine bonds are really, really heat stable and resistant. You might use these on some of your like kitchen appliances if you're heating up or cooking, or things like, you know, Gore-Tex. Those use other combinations of carbon and fluorine. So those bonds are typically very resistant to degradation, let alone some type of nucleophile. So why is it that when we introduce a fluorine in that aromatic group with a nitro group adjacent to it, that we get that nucleophilic aromatic substitution? So here's the other interesting and puzzling thing. If you take a look at an example like this, where now X is equal to any of those halogens, and if you do that type of reaction, let's call this nucleophile negative, if X is equal to if X is equal to fluorine, chlorine, bromine, or iodine, the rate, let's write this, the rate is much greater when fluorine is used, much, much greater compared to chlorine. Almost never works with chlorine, much bigger than bromine, and much, much bigger than iodine. So it seems to be kind of reverse of what we did with SN2 alkylation. If you do use fluorine, I do want to let you know that this step is very, very slow. Okay, so you get reaction occurring here, push electrons into this nitro group. So here's the intermediate. Break the aromaticity. And there's a large energetic penalty to doing this reaction, right? You're taking a very stable compound, aromatic, and you're essentially breaking that apart. So that's energetically very difficult to do. This is going to be a very slow reaction, but it does work best with fluorine. This is going to be a very slow step. And then lastly, this last step for elimination, as we've seen down there, electrons will come down. This is actually a very fast step because the molecule wants to re-aromatize. That is a much more stable compound. And as we mentioned, that's the elimination. All right, so why does this work with fluorine so much better compared to the other ones? So fluorine is special, as I mentioned, and because it's very electronegative, you have something called an inductive effect. Okay, so it's not that the fluorine is holding a big negative charge, but it is strongly pulling electron density away from this carbon-fluorine bond. So because of this inductive effect, coupled with this electron withdrawing group that is in the conjugate addition of 1, 2, 3, 4, this position here, you have this carbon here that's now very, it's very conducive to electrophilic attack. All right, so inductive effect from the fluorine plus the electron withdrawing character from the nitro group help promote and initiate this reaction. All right, so maybe I'll just write just a brief sentence around about this. So fluorine is very electronegative. And via inductive effect, coupled with the electron withdrawing groups from the nitro group, we can get initial nucleophile reacting at that carbon. If you didn't have that nitro group there, the fluorine group is usually not good enough for that reaction to occur. I say usually because there's always exceptions, but you need to couple it with a strong electron withdrawing group. Okay, so in general, we can summarize this as follows. If we have a fluorine group here, and I'll put a Z group here, and if Z is either ortho or para to the fluorine, so we can put a Z there. And if Z is a good electron withdrawing group, it's possible to get that nucleophilic aromatic substitution. Okay, so what are some good examples of electron withdrawing groups? Well, we just saw the nitro group. Yeah, nitro group's good. We looked at the previous lecture, the nitrile group, right? The nitrile group. So nitro, nitrile. Those have slightly different pronunciations. I mean, this chapter really has been focused about the microreaction. So we go back to our starting carbonyl. Again, that's a good electron withdrawing group. There are many others. I have another one here. This is a sulfonyl group. Anything that can pull electron density away would be quite suitable. All right, so I want to show you, we're going to go through a mechanism of a product called Floxacin, which is an antibiotic that's quite broad-based, but it's quite useful. And it can be used to target various types of bacterial infections. But the way it's made is that it employs a combination of all the chemistry we've learned and applying that nucleophilic aromatic substitution to its synthesis using fairly basic starting materials. So maybe what I'll do first is I'll draw the structure of a floxacin in the lower right-hand corner. We'll start at the left here, kind of work our way down. So if you have a sort of, I would start a new piece of paper and put this in the lower right-hand corner. Let me make sure I get the structure correct. Okay, as I imagine it's an antibiotic. Let me just double check the structure. No, structure is wrong. Okay, so pardon me. Okay, so there's the correct structure. Okay, so that looks better. Double bond, nitrogen, nitrogen with a methyl group. Okay. All right, so it's a compound with a fluorine group attached to it. And I'm going to show you starting material, and I want us to draw a mechanism of how we can get to the final product. Okay, so we're going to start with this compound, and we're going to treat it with this amine here. And I think you can see, based on the final compound, that this nitrogen is going to play a key role in making that second fused ring, and it needs to form like a nitrogen carbon bond and another nitrogen carbon bond. Okay, and then the oxygen needs to eventually react at the other carbon there. So in terms of a mechanism, how would we start this reaction? So your nitrogen obviously is your better nucleophile. And the first thing you can see here is that we have, we can set this up through conjugate addition, substitution reaction. So you can imagine nitrogen comes here, electrons go up, and then later they'll come down. And then this is actually a, good enough leaving group. All right, so let's do that. So this will come up here, push electrons up into that carbonyl group. We have a nitrogen that's positively charged, so we're now simply going to remove a proton with a base. Okay, and then like we've seen with the substitution reactions, electrons will come back down, reform that double bond, and that's your leaving group. All right, so we have 4, so I forgot the fluorine here. So it's a tetra substituted group here. Okay, all right, so far so good. And what I'm gonna do is, I'm just actually gonna draw, and you'll see why in a second. I'm just gonna draw this aromatic group in the other resonance form. And I think it's probably pretty obvious. Well, I hope it is. Because now you have this fluorine group here. Through inductive effect, the nitrogen can attack here. And you can see here that this is actually ortho to this electron withdrawing group, right? So just think back to the rules that we talked about over there. So this nitrogen group can come here, can react right there through the strong inductive effect, move electrons up into that carbonyl. Okay, so we've broken the aromaticity, right? So there was an energetic penalty for that. So, you could argue this is a relatively slow reaction, okay? And you have your positively charged nitrogen. So we're going to go through another proton transfer. This is not a hydrogen, that's just simply a methyl group, so methyl group. All right, so you can see here that we've now set this up for elimination. So the reaction comes down. This is the fast step where now you can kick off the F minus. All right, so what's that going to look like? Let me change my my pen. That's going to look like and I'm just going to draw this group, and I'm just going to rotate this bond here so we have the OH group in that orientation. And you can see why, because we need to form a carbon-oxygen bond. All right, so now this might seem a little unusual because now we have a fluorine group here that is actually meta to this group, and there aren't any good electron withdrawing groups that are necessarily ortho or para, or are there? So in fact, what's postulated to happen is that you get reaction occurring here, and remember, fluorine itself is actually an electron withdrawing group. So through inductive effects here, and through this electron withdrawing character, you can actually, or what's hypothesized to happen is that you form a stable carbanion at that position, stabilize again through that fluorine group. We've broken the aromaticity again, so just remember this is a slow step. We'll put the negative on this group here, okay? And what we're going to do is a quick proton transfer. Okay, it's going to look like this, all right? So kind of analogous to what we've done already. And then what we're going to do is we're going to now have this group come down, reform the aromaticity, and then you'll displace off that fluorine group, all right? All right, so maybe I'll put this in a little box so we don't get that in the way. So we've now displaced off two fluorine groups. Let's see what we've got here. Okay. All right, very good. So we're definitely getting closer to this structure here. We formed the backbone framework. What we need to do is we need to take this ester here. We need to saponify to carboxylic acid. That's straightforward. We'll save that for the end. But what we need to do is remove this fluorine here, replace it with this, like this diamine here. All right, so how are we going to do that? Well, actually fairly easily. We can simply add this molecule here as the amine form, and you can see here that through inductive effects, this is going to be electrophilic, and it is actually para to this electron withdrawing group. And it's also ortho to this fluorine adjacent to it. So through inductive effect and the combination of this, you can actually get fairly good selectivity occurring at that fluorine position. So let's do that reaction. Let's treat that with this compound here. So we're going to now get this reacting here, and we're going to push electrons up into that carbonyl system, like I'm showing you there. Okay, so your amine has reacted. Now the positive charge on here. So you can see I'm running out of a little bit of room, but that's okay. No need to panic. We can just move over here. And what's going to happen is you'll do your proton transfer. All right, so I think that's correct. Just remove that charge, and again, that first step is slow. It's always fairly slow. Proton transfer, of course, is fast. And then the last thing we need to do is this comes back down, push electrons down, re-aromatize the system. F- is your good leaving group. Well, it's generally, like I said, it's not the best leaving group, but because we re-aromatize, in all these cases, that's the driving force for making these elimination steps fast. So it's a bit of a monster to draw each time, but definitely keeps you focused so that you try not to draw errors. Okay, so we're almost done. And you can see here that this is an ester. We're going to do saponification. I'm not going to go through that mechanism. You know how to do that. Saponify an ester to carboxylic acid. And that will leave you with your compound, which is an antibiotic. So it's really kind of a neat mechanism because it takes these compounds and it doesn't really take much for all these different reactions to occur. There's definitely some intramolecular driving forces that help as well, forming these six-membered rings. But using fairly standard and simple building blocks, we can generate this compound. All right, so do I have anything else I wanted to talk to you about today? I think that's good. This I've been talking for 53 minutes or about so. So I think we'll stop this lecture for today. All right, see you for the next one. Take care.